Welcome to the latest edition of C-Step Podcasts. The title of today's podcast is Renewable Energy Integration and Storage, which is being presented by Bishal Mazumdar. Bishal Mazumdar is a research engineer at the Center for Study of Science, Technology and Policy, C-Step. He completed his B.Tech in Materials Engineering from the National Institute of Technology, Durgapur in 2011. Following this, in 2012, he received a master's degree in Energy, Science, Technology and Policy from Carnegie Mellon University, USA. Bishal's core competencies lie in wind and solar integration and energy storage. He has authored several papers in prestigious international journals like Solar Energy, International Journal of Green Energy, and also published articles in mainstream media. He has been with C-Step for over 2 years and is presently working on issues related to grid integration of power generated from renewable sources of energy and energy storage technologies. Could you tell us a little about the problem being faced by India today with regards to power generated from renewable sources of energy and grid transmission?
Sure. So, the Indian power sector has been recently under the spotlights mainly due to two reasons. The first one being its inability to provide stable electricity supply to its more than 1.25 billion population. And the second one is associated with the ambitious targets that the country has with renewable power sources, specifically with wind and solar power. So the popular opinion is that if we can expand on this wind and solar power resources, then we can look forward to a sustainable energy future, right? And in fact, some of the recently published government reports talk about necessary targets of more than 100 gigawatts each for wind and solar by 2030 in our country. So that's really great. That means, the future is really exciting. But there are a hell lot of problems associated with this renewable power sources. And the main one comes due to the inherent intermittency and unpredictability associated with wind and solar power. So what happens is that we do not have a firm control on how the wind and solar power is being produced, because it depends a lot on nature, right? So we also call them as variable renewable power sources. And once we are talking about integrating this significant amount of variable wind and solar power to the grid, we are looking forward to a situation where there will be a huge amount of voltage fluctuations in the grid. And this can cause a huge number of issues related to grid reliability in the future. Another problem is related with curtailment. So what happens is that there is a lack of coincidence between the supply of power from these renewable power sources and the demand from end-use customers. So for example, in case of wind, we have more wind at night when the demand is very low, right? Similarly, during monsoon periods, we have more wind in our country. So because of this, when we have excess wind but the demand is low, we need to curtail wind power. And this curtailment results in increased levelized cost of electricity. So this means that though we have enough resources, though we have enough wind and solar resources in our country, there is a big problem related to matching the supply and demand of power in the grid. So that's the problem that we need to deal with.
Okay. How can this problem or these problems be solved?
Okay, so right now at C-Step, we have a project called Solar Energy Research Institute of India and US, shortly SERIUS. So within this project, C-Step is leading the solar energy integration effort. And within that solar energy integration effort, we have something called energy storage and integration. So that is one of the ways that we can solve this problem of grid reliability due to renewable sources. Now there are three subcomponents within this solar energy integration research workflow. The first one being quantifying variability of renewable power, in this case solar. So what we do in this case is we try to understand, so we collect a lot of data for solar power and wind power also. We do some pre-processing, and then we try to extract meaningful insights. So we subject those data to mathematical characterization, and we try to extract some meaningful insights and develop some empirical models. And so these empirical models will be useful in planning and deciding on what kind of fill-in power sources will be necessary. So battery is one example, storage. So for example, when there is, for example, in case of solar power, if it ramps up when the demand is low, then we can store some of the power in our battery. And later when the demand is high and the solar power is ramping down, for example, then we can discharge the battery and limit the fluctuations. So that is one part of the research. The second one is energy storage analysis. So in this one, recently we completed a study on investigating the scope of energy storage technologies in India. So we investigated 4 different applications. The first one being rural India. So for rural India, we envisioned a case where, we tried to answer the question, are solar PV-based mini grids, can they alleviate the power crisis issue in rural India? So we tried to calculate, or we tried to estimate the scope that storage can play by supporting these PV mini grids in rural India, and this includes both electrified villages as well as the more than 30,000 unelectrified villages in our country. And one of the most important component of this work was comparing the mini grid and storage economics with conventional practices, right? For example, today in rural India, mostly we use diesel for electricity supply. So it's very important to compare these new technologies with the price of diesel so that we can make smarter decisions. So that's what we did, and we compared different battery technologies. For example, sodium sulfur battery, lead acid battery, advanced lead acid battery, or vanadium redox flow batteries. So we compared the costs of PV-based mini grids with different battery technologies, and overall we compared it with the conventional diesel use. Apart from this, we investigated the scope of storage for urban rooftop PV sector, the telecom sector, because the Indian telecom sector is one of the most energy intensive sector, and because of load shedding, it uses a lot of diesel, which results in a lot of greenhouse gas emissions. So we tried to see how much PV can be used to replace this diesel use. But then with PV, we definitely need battery backup so that we can also supply power during evening times. And the fourth application was for the future power grid. So we projected the future power grid based on the targets that we have. For example, some of the reports talk about targets of over 100 gigawatts of wind and solar power. So we tried to figure out, if we really integrate this much of renewable power to our system, then how will the power fluctuations look like in the future? And what role the storage technologies can play in alleviating the supply-demand mismatch of power. And in addition to that, there are some other people in our storage group who are working in fundamental R&D of storage technologies. So all this, like starting from variability analysis, which let us know what kind of fill-in power sources, including batteries, will be necessary. The second one is, what kind of storage is necessary, what is the cost of storage. So this all leads to this fundamental R&D question, where they are trying a number of approaches to decrease the cost. For example, in case of sodium sulfur battery, we are trying to look into corrosion mechanism by using computational material science, and goal is to increase the lifetime of sodium sulfur batteries so as to decrease the levelized cost of electricity. So these are some of the things that we are doing to solve the problem.
Okay, great. And so if you were to look at storage from a policy perspective, then could you talk about one important consideration when the government thinks about introducing storage systems in the grid in India?
Sure. So for the power grid, the most important thing is cost, because unlike electric vehicles, because in electric vehicles also we need storage batteries. So there we have the problem of size. There are size constraints. But in grid we do not have size constraints. We can have as big as battery or as big as any kind of storage technology we want. So the most important metric is cost, right? So any kind of policy, any kind of research approach should keep that in mind, that the goal should be to decrease the cost of the storage technologies as much as possible. Now in India, for the grid, we already have about 5 gigawatts of pumped hydro storage technologies installed, which are under operation right now. And we have identified potential of about 94 gigawatts of pumped hydro storage. So pumped hydro storage, as well as some new battery technologies like sodium sulfur and some of the flow battery technologies, which are cheap. They are bigger in size, but that doesn't matter in case of grid. But they are lower in cost, which is more important. So pumped hydro storage, sodium sulfur battery, and vanadium redox flow battery, for example, these technologies can definitely play the role of game changers in the power grid, and we definitely put policies into place. For example, incentives for storage, the people who deploy storage technologies, subsidies, and a overall national policy framework is necessary so as to facilitate this whole process. Now, for example, in the West, especially in the US, there is something called time of use pricing of electricity. So in that case, you can buy cheap electricity during off-peak times, store it in your battery, and release it when the demand is high, right? Or the cost is high. So those kind of policies increase the value proposition of storage technologies. So in India also, I think we need those kind of policies to be incorporated as soon as possible.
Great. Thank you so much.
Okay. Thank you.